Inferential statistics allows us to make sense of data. The word infer means to draw a conclusion. Thus, we can draw a conclusion about whether texting while driving increases the probability of an accident, opening a bakery an hour early will significantly increase sales, or if the X-sort method of gender selection increases the likelihood of getting a boy or girl. No matter what field you're in, you will need some process for drawing conclusions from data. We use probabilities to take into account chance variation. The two most widely used types of statistical inference are hypothesis testing and confidence intervals. Both types are based upon sampling distributions, which means we want to find out what happens when we repeat the sampling many times. Remember, the inferences you make are only as good as the data you have. So if your data was taken from a convenience or voluntary response sample, or if the experiment is uncontrolled and you have confounding variables that confuse the results, the inference you make will be spurious or suspicious. In this lesson, we will talk about confidence intervals, a range of values for which we can be reasonably certain that an event will occur. We may want to know the average number of venti caramel macchiatos a given coffee shop sells each month so that we can ensure that we have enough of the ingredients on hand to decide how much to purchase the next time around. Do people buy more or less in December versus July? In considering this data, there will be some margin of error in our guess. But comparing sales in the last 10 years, we can be reasonably sure plus or minus some amount. Buying an excessive amount and not being able to store the items or having them go bad, or alternatively not buying enough so the customers cannot get their macchiatos and are upset, these could cause significant problems for the store. In another example, if we're attempting to find the mean age of people in the United States, the population is so large, with many people coming in and out of the United States every day, we may never get exact value of mu, the population mean. Each sample we take, no matter how large, will have a slightly different value for the sample mean. Thus, because of sampling error, we cannot expect the sample mean to equal the value of the population mean. Therefore, we need to provide our result with a reasonably accurate estimate with some margin of error. We can find confidence intervals around a proportion, mean, standard deviation, correlation coefficient, or some other point estimate. This interval contains a point estimate and a margin of error. In this way, we can create an interval of numbers and then state how confident we are in that interval. For the proportion, the best estimate is p hat. For the mean, the best estimate is x bar, or the sample mean. And for the variation, the best estimate is s squared, the standard deviation squared. So a confidence interval is a range of results around a value that represents the population. This interval is obtained by finding a value or a point estimate, then adding or subtracting the margin of error, and then stating a percentage of how confident we are in that result. The common percentages are 80%, 90%, 95%, and 99%. The most common percent is 95% confidence interval, and we use that if it's not stated. The formulas for the confidence interval for a proportion, mean, standard deviation are given in this table. So we need to have critical values. The common critical values of Z are given in this table. These are used with the formulas for the confidence interval for proportion and a confidence interval around a mean when the population standard deviation is known. You will use table A3 in the back of the book for critical values of t and table A4 for critical values of chi-square. So for an 80% confidence interval, it's 1.28, 90% confidence interval, it's 1.645, 95% confidence interval, 1.96, and 99% confidence interval is 2.575. Let's try an example of a confidence interval. A study of 420,095 Danish cell phone users found that 135 of them developed cancer of the brain or nervous system. Prior to this study of cell phone use, the rate of such cancer was found to be 0.034% for those not using cell phones. The data are from the Journal of the National Cancer Institute. Construct a 95% confidence interval estimate of the percentage of cell phone users who develop cancer of the brain or nervous system. This is a confidence interval of a proportion, so we need to find p hat, which is 135 over 420,095. the proportion is given as P equals 0.000340. So Q is 1 minus P, or 0.99966. Since we have a 95% confidence interval, we will use the critical value of Z as 1.96. Substituting these values into the formula for the margin of error, we get this number. The confidence interval is P hat plus or minus the margin of error, or 0.0266% is less than P is less than 0.0377%. Let's try another example, but this time for a population mean with sigma known. A set of data of weights of women show that a given sample of n equals 40 women, the sample mean is 146.22 pounds. Research from other sources suggests that the population weights of women has a standard deviation given by sigma equals 30.86 pounds. Find a 95% confidence interval. First, we need to find the margin of error. The critical value is Z equals 1.96. The population standard deviation is 30.86 and n is 40. Substituting these values, we get the error equals 9.5636. Therefore, the confidence interval is the sample mean plus or minus the error, which gives you 136.66 is less than the mean is less than 155.78. In a third example, this time with a confidence interval of a mean with sigma not known, on a test of the Atkins weight loss program, 40 individuals participated in a randomized trial with overweight adults. After 12 months, the mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. Construct a 99% confidence interval. We need to find the margin of error first. This requires a t-distribution table. On the table, the first column are in degrees of freedom, which is n-1. Since we have n equals 40, then n-1 is 39. And since we want a 99% confidence interval, then 1% is in two tails. Go down the first column to degrees of freedom of 39 and across to 0.01 in two tails. This gives you a t-score of 2.708. We compute the margin of error to get the error is 2.055. Now we find the confidence interval using the mean of 2.1 pounds and a margin of error of 2.055. We substitute this in and we get 0.045 is less than the mean is less than 4.155. Since the data is to 1 decimal point, we round this to 0 is less than the mean is less than 4.2. There are some other types of hypothesis testing, but they all follow the same general process. Well, that's it for confidence intervals. Now try some of the homework.